Hi there, my name is Rebecca Schmelzer and welcome back to another segment of Code Week. Today we're going to be looking at an introductory lesson on cryptography. Today we're going to be looking at shift/Caesar ciphers as well as Playfair ciphers, and we're going to look at some implementations in Python for encrypting using the shift cipher. All right, let's get started with the shift cipher. So the shift cipher is one of the simplest and most widely known encryption techniques. It is a simple type of substitution cipher in which each letter in the plain text is replaced by a letter some fixed number of positions down the alphabet. So for example, with a left shift of 3, D would be replaced by the letter 3 positions ahead, which is A, and E would become B, and so on. The method is named after Julius Caesar, who actually used this technique in his lifetime. So let's use this example I've coded out here. The transformation can be represented by aligning two alphabets. The cipher alphabet is the plain alphabet simply rotated left or right by some number of positions. So for instance, here is the Caesar cipher using a left rotation of 3 places equivalent to a right shift of 23 places. So as you can see right here, in the plain alphabet, in the cipher alphabet, the X is shifted to the front of the alphabet, and then it goes down to Y and Z, finishing off the alphabet. As you can see, it's been shifted 23 places, and then the alphabet restarts over at D's position, and it goes all the way down until it reaches the 26th character of the alphabet. So, when encrypting, a person simply looks up each letter in the message of the plain text and writes down the corresponding letter in the cipher line. So, in the plain text, you could be writing this simple sentence, and then to encrypt it, simply look up each letter and transcribe it to get this encrypted message over here. So, the encryption can also be represented using modular arithmetic by transforming the letters into numbers according to the scheme A is equal to 0, B is equal to 1, so on until Z is equal to 25. Encryption of a letter X by a shift N can be described mathematically by the following function. So this is our encrypted letter, and the letter X plus the shift number N mod 26 is actually what gets you your encrypted letter, mathematically speaking. And for decryption, it is this formula, which is the same except you are subtracting your shift number. So before we dive into defining the functions for encryption and decryption in the process of coding the Caesar cipher in Python, we're first going to be looking at two very important functions that we'll use extensively during this process, which is the char function and the ord function seen over here. Now, first we're going to be looking at an introduction to ASCII as well as Unicode to understand these functions. Now, it is important to realize that the alphabet as we know them is stored differently in a computer's memory. The computer doesn't understand any of our English language's alphabet or any other characters by itself. So each of these characters is represented in computer memory using a number called ASCII code, or the extension, the Unicode, of the character, which is an 8-bit number and encodes almost all English language's characters, digits, and punctuations. So for instance, the uppercase A character is represented by the number 65. The B character is by 66, and so on. So similarly, lowercase characters representation begins with the number 97. So as the need to incorporate more symbols and characters of other languages arose, the 8-bit was not sufficient, so a new standard called Unicode was adopted, which represents all the characters used in the world using 16 bits. ASCII is actually a subset of Unicode, so the ASCII encoding of characters remains the same in Unicode. That means that the A character will still be represented using the number 65 in Unicode. And it is also important to note that special characters like space, tabs, or new lines are also represented in memory by their Unicode. So here is a list of ASCII text characters. As you can see, all the uppercase letters, all the lowercase letters, all the numbers, and special punctuation and weird characters. So ASCII, again, is abbreviated from American Standard Code for Information Interchange. And like I said before, it is a character encoding standard for electronic communication. ASCII codes represent text in computers, telecommunications equipment, and so many other kinds of devices. Most modern character encoding schemes are based on ASCII. ASCII uses 128 different encoding combinations of a group of 7 bits to represent characters A to Z, again, A to Z, both uppercase and lowercase, and the special characters seen here. So now let's take a look at the ORD function and the char function. So the ORD function in Python accepts a string of length 1 as an argument and returns the Unicode point representation of the passed argument. So in this example that I've written out here, passing in the character B in the ORD function returns 66, as that is the Unicode point value of the character B. Now for char, this function actually does the exact opposite. You will pass in a number, for example 66, and it will return the Unicode character that is attached to it. In this example, it is the character uppercase B. So now let's actually take a look at the algorithm for the shift cipher. Now, as I said before, the Caesar cipher technique is simple and easy method of encryption. So it is a simple substitution cipher, and each letter of plain text is replaced by a letter with some fixed number of positions down the alphabet. So now let's actually take a look at the encryption function that I have defined here. So first what we're going to do is we're actually going to define our function, and it is going to take in 2 parameters. One is the text, which is going to be the string that we want to encrypt, and the second one is going to be the shift number n, or s in this case, that we want to shift the alphabet down to create our cipher alphabet. So first, what we're going to do is we're going to define a resulting string, encrypted string, at the beginning before our for loop to actually append and attach to our encrypted characters after we do these functions. So this is going to be our ending resulting string. So first what we're going to do is we're going to traverse the plain text. So we're going to set up a for loop for I in range the length of the text, okay, and we're going to assign each iteration of I as a character, as a variable. So basically for every single time the loop iterates, we're going to be looking at each character of the string. So what we're first going to do is the plan for this function is to divide the string into uppercase letters and lowercase letters. So first we're going to see if the character at hand during this iteration is an uppercase letter. So char.isUpper. IsUpper is a function that is used for strings in Python to check if the character at hand is an uppercase letter or uppercase letter. That's what it is. That's what it's used for. So if this condition is passed, if char.isUpper, if the character at hand is an uppercase, we're going to do this calculation right here and append whatever we get to our resulting string. So first what we're going to do is we're going to find the ordinal of the char at hand. So we're going to first find the number, the Unicode number attached to this character. We're going to add the shift and subtract 65 because, again, like I said, this is if the character at hand is an uppercase letter. And like I said before, the uppercase letters begin representation with the number 65. So that's why we're subtracting 65 here. And then, like I said up here, we have to do that mod 26 here. So we're doing that mod 26 here, and then we're adding 65 again to balance out, and then we're finding the character. We're converting it back to an actual character to attach it to our resulting string. So that is the function. This is the calculation that we're doing here for uppercase letters. Now, if this condition is not met, then we have to do something for the lowercase letter. Then it is obviously a lowercase letter. Now we're going to do the exact same calculation here, except it is not 65 this time, it is 97. As like I said before, lowercase characters representation in Unicode begins with the number 97. So we're going to find the ordinal. We're going to add the shift. We're going to subtract 97. We're going to do the mod function. And then we're going to add 97 again. And we're going to convert that back into a character and append it to our resulting string. And then after this entire loop has iterated, we're going to return our result. So here we can actually see, I've set up some testing that we can actually see. So if we can run this, here we are. Okay, so the text that I've given it is the Caesar Cipher demo. Now, obviously, spaces are ignored, and the shift that I've given is 4. So as you can see here, every character in the resulting encrypted text is shifted 4 letters down. So C turns into G, A turns into E, E turns into I, and so on. And this is exactly how we get our encrypted message. And I've also done another example with my name. So R turns into V, and especially, again, it's the same, excuse me, it's the same shift number. So R turns into V, E turns into I, and so on. So that is all we have for the shift cipher. Now we're going to take a look at the Playfair cipher. Now I don't think that we have time to actually go through all the code, but I will go into extensive explanation on how the Playfair cipher actually works. So the Playfair cipher was the first practical digraph substitution cipher. The scheme was invented in 1854 by Charles Wheatstone, but was named after Lord Playfair, who promoted the use of the cipher. In Playfair cipher, unlike traditional cipher, we encrypt a pair of alphabets, digraphs, instead of using a single alphabet. So basically, for the shift cipher, we only use one alphabet, but for Playfair cipher, what makes it more complicated, what makes it more difficult, is that we are using 2 alphabets. So now we're actually going to go through the algorithm with an example. So the algorithm consists of 2 steps. The first step is to generate the key square, which is going to be 5 by 5. So the key square is a 5 by 5 grid of letters that acts as the key for encrypting the plaintext. Each of the 25 alphabets must be unique, and one letter of the alphabet, usually J, is omitted from the table, as the table can hold only 25 letters. So if the plaintext contains J, it is usually replaced by I. So the initial letters in the key square are unique letters of the key in the order in which they appear, followed by the remaining letters of the alphabet in order. So in this example, the key that I've chosen is monarchy. So thus the initial entries are going to be MONARCHY, and followed by the remaining characters of A to Z except J in that order. So as we can see, I've defined this key right here. It's 5 by 5. Obviously, you can see the beginning key is right here in the first 2 lines, and then it proceeds to go down with the rest of the alphabet until the square is filled. So that's our key square. We've defined that. Now, the second part of the algorithm is actually encrypting the plain text. Now, the plain text is split into pairs of 2 letters, digraphs. If there is an odd number of letters, Z is attached to the last letter. So, in the example that I've chosen the plain text to be a string instruments, and since it is an odd number of letters, we have added Z into the last split, and so that it will all be an even number. So now we get into the actual rules for encryption. So the first rule is if both letters are in the same column, then we have to take the letter below each one and going back to the top if at the bottom. So for the first digraph ME, the encrypted text is going to be CL. Let's see here why. Because M is located here, E is located here, they are both in the same column, and therefore we're going to take the one below each. So C is right below M, so M is going to turn to C. L is right before E, so E is going to turn to L. So that's the first rule. The second rule is if both letters are in the same row, then we have to take the letter to the right of each one, and going back to the leftmost if at the rightmost position. So for the digraph ST, we're going to look at find their positions first. So S and T are right here. So since they're in the same row, we're going to choose the ones right next to them to the right. And that's going to be how they become encrypted. So S is going to turn into T as it's right next to each other. And since T is at the edge, there are no more letters here. We're going back to the leftmost, and T is going to become L. So that's the second step. Now, if neither of the above rules is true, we have to form a rectangle with the 2 letters and try to take the letters on the horizontal opposite corners of the rectangle. So, for example, this string that we have here, NT, the encrypted text is going to become RQ, and let's see how that happens. So N is, let's find N. N is here, and T is here. So since they are not in the same row or the same column, we're going to form a rectangle, with them, and they're going to become the ones in the row. So since this becomes a rectangle with R and with Q, N is going to become R, and T is going to become Q. And that's how we encrypt that way. So those are the 3 rules of encryption. So let's put it all together and summarize how we can encrypt an entire string like instruments with a Z. So let me just adjust this so we can see everything. Okay, so obviously we're going to split this entire string into sets of 2, and then we're going to encrypt that way. So IN, so we're obviously starting with IN. Where is IN on our key? I is here, N is here. So since they are not in the same row, the same column, we have to form a rectangle. And so I is going to form a rectangle with G, with N, and with A. So I is going to become G, and N is going to become A. So that's it for IN. For S and T, we've already been through this. S and T are in the same row, so S is going to become T, and T is going to circle back around and become L. Now, moving on to RU, whereas our R is here, and U is here. So we're going to form a rectangle with the entire key. So R is going to connect with M, going to connect with U, going to connect with Z. So R is going to become M, and U is going to become Z. So that's it for RU. And then for ME, we've already been through this. Since they're in the same column, we're going to choose the ones directly below them. So M is going to become C, and E is going to become L. Yes. So for N and for T, again, I think this is another rectangle. Yes. For N is here, T is here. We're going to form a rectangle with these. N is going to become R, and T is going to become Q. Now, for the final 2 letters, S and Z, where are S and Z? S and Z are right here. So this is where S is, this is where Z is. Now, since they are not in the same row or in the same column, we're going to have to form a rectangle with the surrounding elements. So S is going to become T, and Z is going to become X. And that is it. That's our entire encryption. So after following all these rules, we end up with a string that's encrypted that's this. So yes. So remember, our key text was monarchy. We used that key to form a key square that we're going to use to actually encrypt our text. So that was our key. Then our plain text was instruments. We had to add another letter because it was an odd number of characters. And then our ciphertext ended up being this after we encrypted it using all these steps. Now, since I don't actually have time to go through all of the entire coded algorithm, but I can show it to you. It is obviously a lot more complicated than the shift algorithm. There's a lot of code involved, but yes, this is all the code for the Playfair cipher. But yes, obviously the Playfair cipher is much more complicated, but it is actually a lot more efficient. It was actually used for tactical purposes by British forces in the second. Actually, by British forces in World War I, and for the same purpose by the Australians during World War II. This was because Playfair cipher is actually reasonably fast to use and requires no special equipment. As you can see, we just explained it and we just figured out how to encrypt. So yes, I think we are almost out of time, and I hope you were able to learn something and enjoy this lesson. And thank you very much for listening. Bye.